This is a short lecture on the discoveries of two molecules in space. It will focus on the methods that were used to discover the molecules and will contain a brief discussion of the current theories about how life may be formed in space and the implications the discoveries of these two molecules have for these theories. So, what molecules have been discovered so far? Over 180 molecules have been discovered in space. However, almost all of these molecules, with the exception of fullerenes, glycine, and isopropyl cyanide, have linear backbones. This means that they are quite simple molecules which generally could not, by themselves, form any kind of organic life. The discoveries of glycine and isopropyl cyanide are significant both because of their complexity and because both molecules are essential for the formation of organic life. Glycine was discovered in the coma of the comet Wild 2. The coma of a comet is an envelope of dust which originates from the comet and forms when it heats up, for example, when it passes the sun. Isopropyl cyanide was discovered in Sagittarius B2, a star-forming region 27,000 light-years away from Earth. In 2009, the amino acid glycine was discovered in samples from the comet Wild 2, which were collected and returned to Earth by NASA's Stardust spacecraft. As the spacecraft passed through the coma, a collection container was opened, as you can see from the first picture on the slide. The collection container was lined with aluminium foil and aerogel, which captured particles of the gas and dust from the comet's coma. In the picture of the representation of the aerogel, which are the green rectangles, the lighter green dots on those rectangles represent the dust particles. The container was parachuted to Earth in 2006 and the foil samples were analyzed. The foil samples will pass through a hot water extraction and acid vapor hydrolysis procedure to determine the molecular structure of the comet's coma. Glycine was found on both sides of the foil, but was more abundant on the aerogel side, which suggests the aerogel side was the side facing towards the comet, and this suggests that it originates from the comet. In 2014, the branched alkali isopropyl cyanide was detected in Sagittarius B2, a massive molecular cloud of gas and dust located around 300 light-years away from the center of the Milky Way galaxy. Sagittarius B2 is the largest star-forming region in our galaxy and consists of north, middle, and south sections. Isopropyl cyanide was detected in the northern section using the ALMA telescope, a large telescope located 5,000 meters above sea level in Chile. Located in the Atacama Desert, because the lack of water vapor, clouds, radio interference, and light pollution is the perfect place to receive millimeter and submillimeter waves from space, which contain a massive information about stars and planets thousands of light-years away. Analysis of spectral line surveys and previous signal dish surveys from Sagittarius B2 performed by ALMA confirmed the existence of isopropyl cyanide. It was found that the production of isopropyl cyanide resulted mainly from the reactions between cyano radicals, which are pulled around by gravitational forces in the dust cloud, with 2-propyl radical. The recently developed model for astrophysical gas and ice chemical kinetics and layering was used to simulate the chemical process, the formation of isopropyl cyanide in space. It was determined that isopropyl cyanide mostly forms on or inside dust grain ice at temperatures between -220 and -200 degrees Celsius, and it was found that isopropyl cyanide is just as abundant as the other less complex linear molecules from the cyanide family. This is significant because it indicates that complex molecules are more likely to form in star-forming regions, where molecules and gases interact in intricate chemical processes. The abundance of isopropyl cyanide suggests that complex molecules may be the norm rather than the exception in space. It also demonstrates that these complex molecules can survive in harsh environments in space. The discovery of complex molecules in space has enormous implications for theories about the formation of life. It has been speculated for many years that very complex molecules could be released from the coma of comets. The discovery of glycine in the coma of Comet Wild 2 adds credence to these theories. This discovery is also significant because comets are a representation of pristine molecular material, and they give an insight into the type of organic material which may have formed billions of years ago. Study of this material is vital for an understanding of when, where, and how organic material forms in space, and for how long and through what conditions this material can survive. It has been theorized that comets were key contributors of organic material to Earth, and that some of this organic material survived the impact with Earth and likely contributed to the formation of life here. If scientists were able to predict the types of organic molecules that would form in certain types of comets or star-forming regions, then it would mean that scientists could predict where else organic life may have formed in the Milky Way galaxy. It has been theorized that complex molecules essential for organic life are more likely to form in regions of star formation where there exist sufficiently complex chemical reactions than in less active areas. The discovery of isopropyl cyanide adds validity to this theory. The detection of the N-butyl cyanide, the three-branched alkali of this family, could validate this theory. The discovery of isopropyl cyanide also confirms that complex molecules can survive in the harsh environment of star formation. This has significant implications, not only because it suggests that organic life could form around stars in these regions, but also because many comets originate from star-forming regions. This means that molecules formed in these regions, which are essential for organic life, could be spread thousands of light years across the galaxy by comets. Molecules discovered in comets that have impacted with Earth could have originated in star-forming regions millions of light years away. Star-forming regions hold enormous potential for the creation of organic life, both in these regions and throughout the galaxy. The picture on the slide is an artistic representation of a star-forming region, and it includes many of the molecules which have been discovered in space today. While discoveries of glycine and isopropyl cyanide are important, more research is needed to concretely prove the theories they add credence to. Investigations into the organic makeup of other comets and of the chemical processes at work in Sagittarius B2 would significantly contribute to the current understanding of the processes in space for the formation and distribution of complex molecules essential for life